Hello everyone, this is Dr. Karthika from Department of Biomedical Engineering. Today we are going to discuss about magnetic resonance imaging and biomedical images. First of all, what do you mean by MRI? Why do we need MRI? Okay, let's begin here. Magnetic resonance techniques, we have nuclear spin phenomenon and also we have electron spin phenomenon, and here in this nuclear spin we have NMR, that is nuclear magnetic resonance imaging, echoplanar imaging, functional MRI, magnetic resonance spectroscopy, MR spectroscopic imaging. While coming into electron spin phenomenon, we have ESR or EPR and electron spin resonance, electron paramagnetic resonance, and we have ELDOR, electron double resonance, and we have ENDOR, electron nuclear double resonance. Okay. Here we are going to discuss about magnetic resonance imaging. Here, see here the first one. It shows the MRI machine. We have 40 magnet RF coil inside and we have gradient coil inside. See here how the equipment looks like. We have our magnetic field B naught, RF coil, gradient coil, and we have a permanent magnet. Here in the scanner electronics, we have input and output devices, and also we have amplifiers to enhance the signals. See, the first one is magnet, second one is our gradient coil, and third one is our radio frequency RF coil. Okay, what are the main components of a scanner? Here we have static magnetic field coils, gradient magnetic field coils, magnetic shim coils, radio frequency coil, subsystem control computer, data transfer and storage computers, physiological monitoring, stimulus display, and behavioral recording hardware also we have. See here it describes how the magnets and coils present in the scanner. We have main magnet in both sides, and we have coils, RF coils, and we have gradient and shimming. We have control computer. It can control the transmit and receive operations. Okay, here see here the first main magnetic field B naught. The purpose is to align H protons in H2O, little magnets. See here the poles south and north are mentioned here. Here the main magnet and some of its lines of the force. First one. Second one is little magnets lining up with the external lines. Here we can consider the lines of force too. See here, main magnet and little magnets lining up. Okay, and we have some NMR properties here. And first criteria is it must have odd number of protons or odd number of neutrons. Why means it is impossible to arrange these nuclei so that a zero net angular momentum is achieved. Thus, these nuclei will display a magnetic moment and angular momentum necessary for NMR. Okay, here I have listed some examples for your reference. Kindly go through it. Okay. The main thing is angular momentum. It is represented as J equal to M omega, that is M equal to V, M omega, M VR, omega equal to VR. See here how J represents, angular momentum represents, and we have V, M and R. Here the magnetic moment mu equal to gamma J, where here gamma is the gyromagnetic ratio and it is a constant for a given nucleus. And first we have to consider protons. Here what is the role of single proton? There is an electric charge on the surface of a proton, thus creating a small current loop and generating magnetic moment. The proton also has mass, which generates an angular momentum when it is spinning. Thus, proton magnet differs from a magnetic bar in that also possesses angular momentum caused by spinning. See here, protons in a magnetic field. Parallel means it has low energy. Anti-parallel means it can release high energy. See here how it looks like for low energy and high energy. And protons aligned with the field, we have longitudinal magnetization and transverse magnetization. We have outside magnetic field, it is randomly oriented in the outside, and the inside magnetic field, we have applied magnetic field and we have magnetic flow. See how magnetization looks like in longitudinal and transverse magnetization. Here the net magnetization M equal to C B naught by T. See here, net magnetization. And we have a spin system before irradiation. We have lower energy as well as higher energy based on the spin alignment. The effect of irradiation to the spin system, we have lower as well as higher energy levels. Okay, spin system after irradiation, we have after irradiation. See here in the previous slide, we have to equalize lower and higher, and after irradiation the lower level is increased because the irradiation is actually occurred, so the level become lower. Here, see here the RF excitation on resonance and off resonance. See how it looks like in on resonance and off resonance. In on resonance, it rotates through the main axis. In off resonance, it goes to off condition, normally ideal condition, but it has some amount of magnetic field inside the coil. See signal reduction via RF coil. First one, signal reduction. When the signal flow into the magnet, the coil is excited and here the magnetic field is produced and we can detect the signals. Okay, see here the signal detection. Signal is damped due to relaxation, and you have to convert the signal into Fourier transform for further processing. See here our input signal and signal damped due to relaxation, and finally we have our Fourier transform output. And relaxation via magnetic field interact with the local environment. See here the rotation of water molecules. See here how it will be rotated and how the signal is extracted from the system. See here our signal and rotation frame signal, and we have demodulated signal, and finally we have the required output based on our input signal. And after all the process, the system will go into relaxation. See here how it will be looks like in relaxation stage. Already mentioned it doesn't have full ideal, but it has some amount of magnetic field. Thank you.